How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at some practice problems for chemical bonds and Lewis symbols. So, number one, which of the following ions has a noble gas electron configuration? So the big thing about noble gas electron configurations is they tend to have 8 valence electrons with the exception of helium. So if we take a look at chlorine, we can find chlorine on the periodic table right here, and we see that it is in group 17, so it has 7 valence electrons. But this little -1 tells me that it has 1 additional electron. So chlorine actually has 8 valence electrons. So it looks like A is going to be our answer, but let's check the rest of them. Oxygen is in group 16, so it has 6 valence electrons. The +2 tells me it lost 2, so it goes from 6 to -2 of them. It has 4 valence electrons, so not going to be option B. Sulfide with the -3, and we'll see sulfur is also in group 16, so it has 6 valence electrons. -3 tells me that it gains 3 electrons, so it has a total of 9 valence electrons, not a noble gas electron configuration. Potassium with a -1. Well, we see potassium is in group 1, so it has 1 valence electron. This -1 tells me it gains 1 more electron, so it has 2, so it's not choice D. Choice E, we're looking at iodine, which has, well, let's see, it's over here in group 17, so it has 7 valence electrons, and its +1 tells me it lost 1 of those electrons, so it only has 6. So A will be our best answer. All right, number 2, which of the following has 8 valence electrons? There may be multiple. So if we take a look at titanium, which is right here, you would expect its configuration to be whatever argon was, its previous noble gas. And then, well, let's see, we're in the 4th period. So then we got 4s2, and then we're going into the 3d subshell. 3d, how many? We got 1, 2. And if it's a +4, that means we lost 4 electrons. So we're going to lose these 2 first, those 2 second. So yeah, looks like titanium +4 will have 8 valence electrons. It'll have the same configuration as a noble gas. Sodium is in group 1, so we know its basic configuration is 2-8-1. So if it lost 1 electron, it now has 8 valence electrons. Take a look at chloride over here in group 17. You would expect its configuration to be 2-8-7, and this -1 charge tells us that it gained 1 more electron. It also has 8 valence electrons. Krypton over here, one of the noble gases. Noble gases have 8 valence electrons except for helium. And then we take a look at just neutral potassium. Neutral potassium is in group 1, so it's going to have 1 valence electron. That is not going to be it. So A, B, C, and D are all good answers. Which of the following atoms would have to gain 2 electrons in order to achieve a noble gas electron configuration? And there may be multiple. All right, so if we take a look at potassium, it's in group 1, so in order to become a noble gas, it would have to lose 1 electron, so it's not this. Well, let's just jump to gaining 2 electrons to get a noble gas. We're talking about anything in group 16, right? Because if it gained 1, 2, then it would have a noble gas electron configuration. So what elements are in group 16? We got oxygen, we got not magnesium, we got sulfur, we got not chlorine. So oxygen and sulfur would be the best options. For which option is the proper definition for lattice energy? And this one's kind of tricky because, you know, what the lattice energy is let's say we had sodium chloride, right? So if we had the solid sodium chloride and we separated it into the separate gaseous ions, the energy associated with that change is considered the lattice energy. Some places you'll see it's the definition of this process going from a solid to the gas phase, and other definitions you'll say from the gas to the solid phase. Whenever it's going from a solid to the gas, that is a positive change in energy. You got to put in energy. In the opposite direction, it is a negative change in energy. So really either definition kind of works. You want to make sure that they're being consistent with what they're saying though. So for example, like choice B, the energy required to convert a mole of ionic solid into its constituent ions in the gas phase. Yeah, so this is going to be energy required, tells us it's a positive delta H. So that makes sense. But then if we also take a look at option D, it's the energy given off when the gaseous ions combine to form 1 mole of ionic solid. This is also good because it's saying it's giving off energy, so it's a negative delta H. which is also true for that process. So you'll see it defined either way. All right, just know that if you're going from solid to gas, it's absorbing energy. If it's going from gas to solid, it's releasing energy. All right, number 5, we've got a diagram below. It's Born-Haber cycle for the formation of crystalline lithium fluoride. Which energy change, which step number, corresponds to the electron affinity of fluorine? So we got to consider, well, what is electron affinity? It's when you gain 1 electron. And the energy for that tends to be a negative delta H. So we're saying, hey, we start with a fluorine. And what's specific about the definition of electron affinity is it's got to be a single atom in its gaseous state, gaining 1 electron. So we're looking for a step where that changes. If we take a look at step 4, we'll see that. We have fluorine gas with a separate electron, and then it comes together to give us the fluoride ion gas. So yeah, step 4. And you can also see that the step is exothermic. It's giving off energy, which is also consistent with what we know about electron affinities typically. All right, which energy change or step number corresponds to the first ionization energy of lithium? So first ionization energy means we're removing an electron. So it ends up being a separate thing, and it has to be an atom in its gaseous state. So we start with lithium in its gaseous state, we remove an ion or an electron, and we end up with an ion in its gaseous state. So which step is represented by that? I think if we take a look at step 2, you'll see it. We start with lithium gas, we end up with the lithium ion in the gas phase and a separate electron. So step 2 for that one. 7, which of the following options has an electron configuration of Kr4d10? So the kind of shortcut with this is you just go, hey, how many electrons does krypton have? And it's got 36. And then this 4d10 means that there's 10 more electrons. So we're looking for something that has 46 electrons total. So let's check it out. With first option, Ag plus. Well, if I look at Ag, it has 47. And this plus tells me it lost 1. So it has, hey, look at that, 46 electrons. A is looking pretty good. But let's check the rest. Strontium has 38. Plus 2 means it lost 2, so it only has 36 electrons. That's not going to be it. Te plus 2, let's see how quickly I can find Te. Boom. So it has 52, but that plus 2 tells me it lost 2, so it has 50. So that's not going to be an option. Tin Sn plus 2, where is tin? Right there. 50, it has 50. Normally, this plus 2 tells me it lost 2 electrons, so it has 48. So not choice D. Rb plus 1, all right. Rb has 37, but it lost 1 electron, so now it only has 36, right? So choice A. Number 8, what is the abbreviated electron configuration for Fe plus 2 ion? So if I take a look at Fe, it's right here. What I would expect it to be, well, let's see if it's in period 4. Previous noble gas is Ar. So I go, hey, whatever the configuration is for argon, and then we end up in period 4. So I start filling in the 4s. There's 2 electrons, check, check, and then there's 1, 2, 3, 4, 5, 6 electrons that are going to be in the 3d subshell. Now this plus 2, you got to remember always, you lose electrons first from the highest principal energy level. So even though I was like, hey, 4s2, and then we start filling the 3d6, you're going to lose the 2 electrons from that 4s because it's at a higher principal energy level. So the abbreviated electron configuration for Fe plus 2 ions, you would expect to be Ar3d6. And last one for this section, which metal would you expect to have the greatest lattice energy with a chloride ion? So chloride ion, we got a -1. The greatest lattice energy, you want the biggest difference in charge. So basically, like if you had a +1 bonding to a -1 versus like a plus, or let's say a -1 with a +3, this is going to be a greater lattice energy. There's going to be more attraction there because there's a greater difference in charge. So cesium's going to have a +1, potassium's going to be +1, sodium's going to be +1, lithium's going to be +1, and rubidium is also going to be +1. Interesting. Well, the difference in charge not helping me out here. So then you also want to take a look at size. Smaller things are gonna be more attracted to each other because they can get closer. So which one of these is the smallest one? It's gonna be lithium. So choice D. All right, I hope you found it helpful. See you in class. Goodbye.